Okay, so it seems that the number of participants has converged. I suggest that we get started. And thank you again for agreeing to give your presentation at this uncommon time. Guiseppe Rosario Del Sorbo is a third-year student, as he's indicated on his screen, and he will be speaking to us about understanding viscosity changes in polyelectrolyte surfactant complexes.
Okay. So, hi everyone, I am Guiseppe Rosario Del Sorbo. I am a third-year PhD student, and my PhD project is based on a collaboration between ILL, where my supervisor is Ingo Hoffmann, and the Max Planck Institute, where my supervisor is Emanuel Schneck. And today I'm going to tell you something about the understanding viscosity change in polyelectrolyte surfactant complexes. So, at the beginning, I will just give you a brief introduction to see what polyelectrolytes are, and after I will focus on polyelectrolyte surfactant complexes, and I will try to explain you how I studied these complexes, and at the end we will also see some results from the molecular dynamics simulations that are part of this project too. So for instance, we can say that a polyelectrolyte is any macromolecular material which is charged, and we can have different kind of polyelectrolyte based on the origin, on the composition, or on the charge. And we can say that we use polyelectrolytes basically in our life because they have a lot of applications, for example, in biomedical technologies, in cosmetic, or even in wastewater treatment. Now, if we just switch directly to this project, the polyelectrolyte which I used during this project is JR400. This polyelectrolyte is a cationic cellulose-based polymer, so it has a positive charge, and this positive charge is on the 27% of the glucosic unit. By the way, we are interested in the interaction between the polyelectrolyte and the surfactants, where a surfactant, we can say that is any amphiphilic molecules, which has an head that is hydrophilic and a tail which is hydrophobic. Now, when we mix a polyelectrolyte and a surfactant, we get a solution. And this solution, basically, we can have different compositions. And a parameter that is able to describe the compositions of our solutions, it could be zeta, where zeta is the ratio between the charge on the polymer and the charge on the surfactant. Now, when we prepare these solutions, the first thing that we see is a phase diagram. And as you can see in the slide, when you prepare a sample with high value of zeta, that means, so in this part of the graph, that means that in our sample, we have a lot of a polymer and just a bit of surfactant, the solutions will be clear and homogeneous. But if we start to decrease zeta, and so you add more surfactant, at some point you will be in the two phases region in the phase diagram. So you have a precipitation in your sample. And if you decrease more zeta, so you go to very low value of zeta, that means that you have a lot of surfactant and now a bit of a polyelectrolyte, your solutions will be clear and homogeneous again. But now the question is, why these solutions are so important? So first of the thing is that when you work with these solutions, they are able to form complexes at very low concentration. In fact, the critical aggregation concentration of these solutions is even below the CMSC of the surfactant. And if you change, for example, the polyelectrolyte, the surfactant, or even the solvent, you are able to get a complexes with different structures. And for this reason, we used for all the time the same polyelectrolyte, but we only change the surfactant. And the two surfactants on which I'm working on are SOS and STS, where they have the same head group, which is an sulfate head group, but they only differ in the length of the tail. Because with SOS in the tail we have 8 carbon atoms, while with STS in the tail we have 14 carbon atoms. Okay, we prepared these solutions. The first thing that we can see is the phase diagram. And as you see here, when we work with STS, you have the two phases region that is centered to zeta 1, where zeta 1 basically means that we have the same number of charges between the polyelectrolyte and the surfactant. But when we work with the SOS, this two phases region is shifted, and it's shifted to a low value of zeta because it's centered at 0.1. But actually, this is not the only thing that you see when you prepare these solutions, at least in a macroscopic way, because you also see a difference in the viscosity. And so we measure this viscosity. And as you can see here in this slide, basically when you work with SOS, you see that the viscosity is not too much different from the viscosity of the poor GR400 solutions. And when you move from high value of zeta and you try to approach the phase boundary, as you can see here, this viscosity is almost constant, is not going to increase. While with the STS, as you can see here, we have a trend. And if we just look better at the viscosity of just STS, you can see that moving from zeta 10 to zeta 3, that means that we are super close to the phase boundary, this viscosity increases by several, actually it's 3 orders of magnitude. So we have a great effect on the viscosity. And for this reason, it makes sense that when you work for rheology measurement, we just work on STS, because with SOS, as we already saw, the viscosity is not too much important. So at this time, I already introduced the concept of viscosity. But what is a viscosity? Basically, when we talk about a viscous material, it's just a material which has a resistance to flow. But we can also have an elastic material, because there is viscosity and elasticity. And if we combine viscosity and elasticity in the same material, then we can have a viscoelastic material. Now, we have to think that this viscoelasticity basically is related to the microstructure that we have in our sample. And when I say that the sample has a microstructure, means that in the sample, there are forces between particles, molecules, or chains that they are holding together. And the way to study the microstructure and so the viscosity with the areometer is with the frequency sweep measurement. Basically, you have your areometer, you have a sample between two plates where the plate on the bottom is fixed and the plate on the top is able to rotate. You fix the amplitude and you just change the frequency in the range of this amplitude. And what you get from this measurement? From this measurement, you get two important parameters, G prime and G double prime, where G prime basically takes in account for the elasticity of the material, and G double prime takes in account for the viscosity of the material. So now we can have a look at this rheology measurement. And as you can see here, we have the graph basically divided into parts, because at high frequencies, G prime is higher than G double prime, while at the low frequency, G prime is basically lower than G double prime. But this is what does it mean? When we have that G prime is higher than G double prime, so we are in this part of the graph, it just means that we are applying a force to our sample, but this force is not higher than the force in the microstructure. And so the sample basically is able to store energy. And when we remove this force, it's a kind of able to be back to the equilibrium position. But when we are here, and so G prime is less than a G double prime, the force that we are applying is higher than the force in the microstructure. And so basically the mechanical energy that we give to the material is dissipated, the material flows, basically it behaves like a liquid. But what we see in this graph, and the thing that is really important, is the point of a crossover between a G prime and G double prime. Because this point actually gives us a super important parameter, that is the relaxation time. And this relaxation time basically is a kind of identikit of our material, because it's the times that the material needs to be back to this equilibrium. And it's related to the microstructure. Now we can understand why. So if we measure this tau cross relaxation time for the same sample, but for different value of zeta, you can see that basically tau cross increases as more surfactant is added. And if at zeta 3, that means that we are super close to the phase boundary, we have the highest value of tau cross, It just means that here, in this sample, we have a well-defined microstructure. So now we want to analyze this microstructure in a better way. And so we did SANS measurement. Just to remind us some theory concept about SANS, here in the slides, I just have two different curves for two different objects with two different shapes. Basically, when we fit our data in SANS, we are just fitting the data with the model. And we know, for example, that when we have a Q-1 slope in our curve, this Q-1 slope is related to a cylindrical object. All this information about the shape of the objects are in the equation that is on the bottom of the slide. And in this equation, we have two important factors, the form factor and the structure factor. Now, just to touch in a very easy way the meaning of the form factor and the structure factor, we can think that if in our solutions we have an object, and this object is made by elementary scatters, when we talk about the form factor actually comes from the interactions, the interferences, basically, the interferences of the elementary scatters which belongs to the same object. But of course, in the solutions, we have different objects. And if we have different objects, we can introduce the structure factor. So we have different objects, and the structure factor now, it still comes from interferences of elementary scatters, but at this time belongs to different objects. And so now we can understand that the information of the object is inside the form factor. So if I start to introduce my data, and we start with the poor JR400 solutions, now we understand when I say that I fit this data with a cylindrical form factor. And what I found in analyzing this data is that this cylinder has a radius of 0.6 nanometer and a length of 6 nanometer. But of course, we have two different surfactants. So we can have data with SOS. And when we work with SOS, as we can see here, well, life is not going to change, because it seems that for all the time, we just are looking the JR400. The curves with SOS is not much different from that one of the poor JR400 solutions. Well, of course, the intensity at low Q is going to increase, but it's just because we have more stuff in solution. But when we work with STS, the situation is different, because now, as you can see, when we have the surfactant in our solutions, the curves is totally different from that one of the poor JR400 solution. So at this point, if we just stress this concept with STS, and we are at zeta 3, where zeta 3 means that we are in the solutions close to the phase boundary, we can just have a look at the curve, and we can see that at a very low value of Q, we have the structure peak. In the middle Q, we have the Q-1 slope that is related to the shape of our rod-like aggregates. And here, at a very high Q, we have basically the contribution of the free polyelectrolyte in solution. And so we can estimate the radius of our polyelectrolyte. But now, just to better see the difference between SOS and STS, if we compare these two surfactants at the same zeta, that is zeta 5, we can see that when we work with STS, basically, we have this well-defined Q-1 slope. And if we have this well-defined Q-1 slope here, we can say that the surfactant that acts basically is a kind of cross-linking between two different polyelectron chains. It connects these two different polyelectron chains with the rod-like aggregates. But we cannot say the same thing with SOS. So what about the organization of SOS around the polyelectron chains? So for now, I keep this question open, and I will be back on this when I will introduce you the molecular dynamics simulations. By the way, when you work with the SANS, one of the most powerful things is that you can work with the contrast. And if you change the contrast, basically you are able to switch on, switch off the stuff that you have in solution. So when you work in bulk contrast, you're just able to see all you have in your solutions. But when you work in polyelectrolyte contrast, you only see the polyelectrolyte. And when you work in surfactant contrast, you only see the surfactant. So you're just able, to have basically a better image of the shape of your samples or your objects that you have in solution. Now, when you do this experiment, of course, you are able to fit these three curves together, and you can get more information. And if you just think at the cross-section of the rod-like aggregate, fitting this data, we are able to describe them as a core shell. So we found out that we have a core in which we have the surfactant and some polyelectrolyte, and we have a shell made only of polyelectrolyte. I have to say that from previous work, actually, these data were fitted with a similar model, but there was another additional core in the middle, and this core was made of only surfactant, but this core was super tiny. So this tells us that it's not a big issue. Basically, it's not, an error if we just fitting this data with a model in which we have one core. But at this point, we can also have an information about the diffusion of this aggregate. And if we want to see the diffusion of this aggregate, we need to have a look at the spin echo measurement. So on the analysis of this data, we are working right now. So I can just give you a qualitative information, not a quantitative one. But here, basically, we can see the diffusion of the polyelectrolyte, just the pure polyelectrolyte. We can see when we work with the STS, the hydrogenated STS, we can see the diffusion of the aggregates. And you can see that at high value of Q, this diffusion is still dominated by the JR400, by the polyelectrolyte. And when you work with the deuterated STS, basically at lower Q, you still see the aggregates, that they are not perfectly matched out. And in the middle part, so in this part, we are able to see the part of the JR400 which is inside the aggregate. Now, of course, the question is if this polyelectrolyte, which is inside the aggregates, is free to move or is kind of fixed. But to tell this, we should analyze this data. For now, we just saw that the information that we got from the first part of the analysis related to the radius and the length of the aggregates is perfectly agree with the result that we got from SANS data. At this point, so just to analyze the last part of this presentation, we can have a look at the molecular dynamics simulations data. I have to say that from these molecular dynamics simulations data, we have basically a lot of systems. We analyzed a lot of systems, but now I'm just going to show you some pictures that will help to understand us the result that we get from the experimental data. And this first set of simulations is with just one chain of a polyelectrolyte. So we have one chain of a polyelectrolyte with SOS, and now we should have a video that I hope it should work, that basically we can see in this video just how the molecules are moving around the chain. And the first thing that we can see is that when we work with SOS, we have these free molecules that are not attached to the chain. But to better understand the organization of SOS along the polyelectrolyte chain, we need to compare this with STS. So now we have the situation with STS. Also here, we should have a video that it should work, okay? We can see that basically also here, the molecules are moving. But the first important thing that we see is first is that we don't have free molecules. And the second thing is that now we have this aggregate that we don't have with the SOS. So we have a well-defined aggregate on the chain, while with SOS, basically, as you can see here, we have more kind of homogeneous distribution. But there is a way to better understand this difference between SOS and STS. So if we just switch on the snapshot, where probably the difference is better, we can start to show some analysis of these molecular dynamics simulations. I will not go in details because, I mean, otherwise we need too much time. But what we can do with this result is to calculate the cylindrical radial distribution of the methyl atoms that belongs to the surfactant around the backbone of the polyelectrolyte. So we are just saying that, okay, we are considering the backbone of the polyelectrolyte, we are at a distance, and we are just looking at the probability at this distance to find a methyl group. As you can see here, when we work with SOS, basically, we just have these two peaks. That means that the SOS is closely bound to the polyelectrolyte. But when you work with STS, we have this third peak. This third peak means that we have some methyl that are indirectly adsorbed to the chain. What does it mean that they are indirectly adsorbed? It just means that these methyl groups basically are part of those large aggregates that we have with STS, that we don't have with SOS. So now we can reply to the question, how is the organization of SOS around the polyelectron chain? We can understand now that when we work with SOS, basically SOS is more individual attached. We have molecules attached to the chain, while with STS we have aggregates attached to the chain. And it's also true that with SOS we have some free molecules. And this is consistent with the analysis of the data, because we saw from the analysis of the SANS data that basically some SOS is free in solution. At this point, we can move to the analysis with the two polyelectron chains, and here we just see the snapshot. So when we work with SOS, again, we have free molecules in solution, and the polyelectrolyte is homogeneous distributed, and is very homogeneous between the two chains. But now if you work with STS, the situation is different. And as you can see, we can define this, aggregate, and these actually are the rod-like aggregates that we are able to extrapolate from the SANS analysis. So at the end of this discussion, hoping that the message was clear, we can say that the viscosity of these complexes increases when we approach the phase boundary, at least for STS. It's also true that when we go to the phase boundary, the mixed aggregates are formed, they are the interconnection between the polyelectron chains. The contrast matching shows that we can describe the cross-section of this aggregate with a core shell mode. And it's also true that for molecular dynamic simulations, we are able to see how the SOS and STS are organized along the chains. The last more thing that I think that I am in time to tell is that, well, most of us of the PhD student, we started together and we are going to finish by the end of the year. And I would like to say thank you to all of them for the time that we had together, because it was great. So thanks for the attention.
Well, thank you very much, Giuseppe. And I really appreciated your presentation. Moritz Freywein, has raised his hand. So go ahead and tune in, unmute yourself, Moritz, and start your video, please, and ask your question to Giuseppe.
Yes, do you hear me?
Yes.
Yes.
Yeah, could you go back one slide, I think, to the molecular dynamics simulations? So this one, no, yeah, in the second chain, with the two chains, right? This went quite fast, but I was wondering, is these irregularities you have in the chain or in the between region, are they connected with the boundaries of the simulations, because it seems very repeating in both sides.
No, I mean, it's just repeating
what I mean?
because, well, this is, when you see in VMD, this is plus zeta minus zeta. So this is the structure that you see, and this is the repeating unit in the simulations.
Yes. So could it be like an artifact of the boundary?
Well, I mean, I didn't show here because I don't want to say a lot of things, but we analyzed this data with the cylindrical, with, I mean, the spherical actually and cylindrical distribution function. And so, I mean, this is the result that I told you is something that we saw even from the data. It's not just the result that we saw from VMD or just from visualizing the data. I mean, there are functions that they describe the difference in the aggregation between SOS and STS. And it's also true that, of course, I mean, those are simulations about 100 nanoseconds, but I mean, it can happen sometimes that this difference is even bigger. That could be, I mean, is not less than this, but it can be even bigger. But this is just the last step, snapshot of the simulations, basically.
And did you see any hexagonal aggregates?
No. Anyway, it's also true that, I mean, the set of simulations is huge because we started from micelles, we start from molecules, we have minimum counter ions, we have the tail counter ions. So it's also true that, I mean, it's just, I guess, here the easiest part to understand in a few minutes, because otherwise it could be confusing if you show.
Yes, I had a brief comment and then a question. I really appreciate your distinction between the structure factor and the form factor, because that can be a bit confusing for some people that don't work with diffraction techniques. And basically, I tend to think of the form factor as intra-scattering center or intramolecular in the case of a molecular liquid, or for example, and that the structure factor is inter-scattering center. In other words, it's the arrangement between the scattering centers. And the form factor is related to the form of the scattering object, which normally is an atom, which is roughly spherical. For X-rays, are going to be a little bit less spherical because there's electron clouds, etc. So that was really good that you pointed that out. And then my question is, yes, so one thing that I've done a little bit of SANS work, and one thing that I've always found a little bit tricky with SANS is that you look for Q dependences oftentimes over a rather narrow span in Q, where one can consider a horizontal axis in Q logarithmically, perhaps only 1 decade, over which you see, for example, a Q to the -1 dependence. And what I can imagine happening is that you could have at a higher decade of Q, a Q to the -2 dependence, for example, and then at a lower decade in Q, you could have a Q to the 0, meaning constant dependence and scattering for some reason. And you have a transition between the two in the middle over roughly 1 decade, which is not that much. And it could look momentarily, so to speak, Q to the -1, but it's actually a transition from constant to Q to -2. And then you also have a distribution in shapes of objects. When considering the Q to the -1 dependence as indication of cylindrical shapes, it's to some extent an approximation. That's fine, there's a distribution. But have you found in your experience that it could also be a transition from constant-like scattering to Q to the -2-like scattering? And do you feel that 1 decade in Q to the -2 dependence is sufficient for a well-defined Q to the -1 dependence, as you pointed out on slide 15, if you want to go to slide 15? You said that that was well-defined.
Wait.
So in your experience, which is greater than mine in SANS.
So the question, so I mean, the observation is very, so what I can reply is that I didn't only measure the samples with the rod-like aggregates, but I also measured the samples in which I have a lot of surfactant. And if I compare the two curves with the sample in which I have a lot of surfactant, then I can see that I have spherical aggregates there. I mean, I can really see the difference between spherical and cylindrical. So, I mean, on my case, I mean, also according with other data and the previous work, when I say that this Q-1 slope is defined, I guess that is a good assumption, because, I mean, when or at least the most of the part of the aggregates are spherical, that is the case in which I have a lot of surfactant in the sample and not this case, I see a different shape of the curve. So I guess that is not a big issue, but I mean.
Okay, I think I agree completely. I think that the fact that you have the contrast, which is considerable between the spherically shaped scatterers and those which are roughly cylindrically shaped, always with the distribution imperfections, etc. That's a very good indication that you have something different, and that the Q⁻⁻1 region of your plot that you're showing corresponds to a cylindrical shape.
Yeah.
And one can also see that there is a rather abrupt, in terms of SANS features, a rather abrupt transition to a sharper, to a steeper slope at about 1 inverse nanometer.
You see,
yes.
you mean this slope? Yeah.
Right. And so that's another good indicator.
Yeah, but this is one, wait, this one, when you see this slope here, this actually, so this part is the contribution of the free polyelectrolyte in solution. Because when you fit the data, you have different kind of contribution. So you have the contribution of the aggregates, basically it goes to fit this part. And also you have some free polyelectrolyte in solution, so that is the contribution of this part. And from here, you can extract the radius of the free polyelectrolyte in solutions that we know from the analysis of the only polyelectrolyte that is as a cylindrical as well.
Okay, that's interesting. But why is it that the Q⁻⁻1 dependence doesn't continue to higher Q? Is it valid only over a certain range in Q in terms of what one would expect from a cylindrical form factor? Because if you're adding additional intensity contribution, one would be adding Q⁻⁻1 with Q⁻², and therefore you would have a higher intensity above 1 inverse nanometer, it seems to me. Why does the Q⁻⁻1 contribution disappear or weaken at about 1 inverse nanometer?
Wait, why should be this? I mean,
if the steeper slope starting above 1 inverse nanometer is due to another contribution,
yeah,
one would expect that it would be added to the Q⁻⁻1.
Yeah, basically we can see here better, maybe. Yeah, okay.
Yeah.
I'm talking about, yeah, I'm talking about, yeah, here, basically. So the question is this going to, is this the decay? It should be higher, do you mean?
Well, I'm trying to think about it, but I think the answer is probably that the rod-like or cylindrical-like Q⁻⁻1 dependence is simply theoretically only valid over a certain region, because if you get to higher Q, you're looking at smaller features, you're looking at roughness.
Yeah, but this is
the surface of the shape of the
but
cylinder, and so it makes sense that it decreases.
Yeah, but this is true that the Q⁻⁻1 slope basically is related to this region of the in the middle region. I mean, this is
okay.
True. Yeah.
So that's the other thing, is that you have a validity. That means that different regions in Q refer to different things, of course.
Yeah.
And if you go to high enough Q, you start seeing the atoms, right? So you start seeing
exactly.
that we measure with thermal and hot neutrons. So yeah, that's just another thing which I guess I wanted to point out. But no. I mean, I think that in SANS, you often have to content yourself with 1 decade of Q for fitting things. But here, I agree that here there's no problem. You know, you can have more difficult situations, but here it's quite clear.
Yeah, sure.
Especially since you have the contrast with the spherical shaped object. So I wasn't being critical. I was just raising this issue that sometimes one has a Q dependent over a limited region in Q.
Yeah, sure.
Okay. I think I just might encourage someone to speak up, since I have a list of everyone. Aline, are you still tuned in? You often have very well reflected questions.
Yeah, maybe Giuseppe. Just to know, but it's very general question about polyelectrolytes. Like you refer to proteins, so do you know about like are you also it's your purpose or your goal, or do you know studies like that use polyelectrolytes to explain like some protein properties, or just very general?
Well, I mean, in literature, well, they use these polyelectrolytes, especially if they are biocompatible, for example, in drug delivery for because sometimes you can have the effect of the charge to attach something to another cell or whatever, or even, I mean, for the cosmetic to bring in solution, so to make something more viscous. So, I mean, they use polyelectrolytes basically, let's say, almost everywhere. Now in details, I mean, for the proteins, to be honest, I was not focused on. But I know that, I mean, they're using this drug delivery system because, I mean, they have a charge, so they have, and also they are polymers, and if they are biocompatible, I mean, they'll be super useful for this, at least for drug delivery. But I mean, more details.
Okay, no, thank you. I didn't know.
Yeah, you're welcome.
Fela, yes, please unmute yourself on your video and ask your question.
Hey, everyone. At some point, you were speaking about contrast variation that you used with suns. I think
yes.
15.
Wait, is afterwards?
No, 16. Yeah, that one. I was wondering, what technique did you use? Was it the exchange of deuterium and hydrogen?
Oh, yeah. So when you work in bulk contrast, basically, everything is hydrogenated. Mm-hmm. So, of course, not the solvent because it's D2O. In this contrast, we work with deuterated surfactant, hydrogenated polyelectrolyte, and D2O. And here, you just do a match of the SLD, that is difference light scattering of D2O, that should be equal to the polyelectrolyte. So you switch off the polyelectrolyte, you switch off the solvent, and just the surfactant.
Okay, this is what I thought. So what kind of information did you deduct? Was it only structural? Or do you see?
I mean, you are able, because the big thing with these techniques that you can fit all these three curves together, because I mean, you are able. And so, I mean, you can better see, I mean, the structure. And so, as I told, if you just think at the cross section of the aggregate, we can see that they have this core shell model. So basically, the aggregate is a mix between polyelectrolyte and surfactant. It's not just surfactant. And this is the perfect way to see this.
Okay, great. Thank you.
You're welcome.
I have a question, Giuseppe, because I'm new to this, to molecular dynamics. How big is your system? Like how many atoms? And you mentioned you ran it for 100 nanoseconds, which is probably like makes it quite heavy to visualize. And I don't know, what system do you visualize?
No, wait, I did the simulations. So I simulate all the systems for 100 nanoseconds. But of course, at the beginning, there's the equilibration. So usually, for example, when I do the analysis, I'm just using the last 50 nanoseconds, of course. In this case, basically, I have a box of 6 per 6 per 10. And usually I have, I started with 60 molecules of surfactant, because 60 is the aggregation number of STS and OSOS. And I have both simulations, which I started from the free molecules or directly with them myself. But 100 nanoseconds is the time of the whole simulations that I simulated. But of course, the analysis is just on the last part.
Okay, so you don't need to visualize the whole 100 nanoseconds.
Well, I mean, I can visualize, but I mean, when I download the trajectory, you see that, I mean, at the beginning, for example, when you see the two parallel chains, the last snapshot is just the output of all the trajectory. So at the beginning, the molecules are just find their position around the chain, and at the end, I mean, you get the result. So it does make sense to work on the first part of the simulations, because I mean, that is the system is working to find the final destination, let's say like this.
And what do you use? Sorry, what do you use to visualize your simulation? Like what program?
The program is GROMAX, and to visualize is BMD.
Okay, thank you.
Yeah, you're welcome. Thank you for the question.
Yeah, I want to ask what software do you use to characterize sans results? SAS-view or something else?
No, I use SASFIT.
SAS-view.
SASFIT.
Oh, okay. Okay, so like I want to learn this software, and can you suggest me how can I learn?
Sorry, can you suggest you how?
Actually, I want to learn this software to characterize sans, and I'm new to it, these things, and I don't know how to.
Yeah, sure. I mean, we can have time to. I can explain you something. I mean, for sure. What I know, I can explain to you. It's not a problem.
Okay, and like, are there any manual or YouTube videos?
Yeah, I mean, so with SASFIT, well, there is a manual. It is a huge manual.
Okay.
Of course, I mean, you can get some information from the manual, but I mean, from my experience, I guess that sometimes when you start with this program, the better way is that at least someone introduce you the program and show you how it works. Because otherwise, if you just want to read the manual, well, you need the time. This is the point. So if someone, yeah, it's better, but it's not complicated. I mean.
Okay. Okay. Thank you.
Yeah, I can. We can be in contact, and I can tell you. I mean, everything. Don't worry.
Yeah, sure. Thank you.
You're welcome.
I think this has been very successful, and I want to thank our two speakers again for making this work so smoothly, giving such good presentations. Thanks to all of you and to the PhD reps for helping to debug the system when we did a few tests, and for staying tuned to make it work smoothly. Thank you again, and if there's no other comments, I will end the session.